Okay, hello to everybody. This is the fifth and almost the last lecture on causality. And as you will see, I've changed slightly my schedule, because we will touch only briefly in the last lecture on next Tuesday, the time series, because I would like to speak a little bit more deeply about the subject, the topic of this lecture, and this will take a non-negligible part of even the next lecture, and the subject I'm speaking about is the concept of counterfactuals. So let's go into counterfactuals, into the counterfactual part, and let me go deep into this. Okay. So let's start with the concept of counterfactuals. And as usual, for every question, for every doubt, for every mistake that you spot, please raise your hand and let me know. But counterfactuals is the way in which usually the human mind deals with the past. The more classical example of a counterfactual that comes in my mind, the first that comes in my mind went from a discussion that I had with my friends some years ago about a particular event, very important for Italian history and culture. What if this had never happened? If Zinedine Zidane, provoked by Materazzi, did not hit him and would not have been sent off, had Italy won the World Championship of 2006. As you know, I'm particularly fond of football, and then I speak usually of football. But the question is, the nature of the question is much more important of the particular situation that we're watching. We usually use counterfactual question, that is, questions that to imagine what could have been happened but for this particular thing that actually happened. Typical counterfactual question that happened to me: if I had taken the freeway, I would have gotten to the church earlier. That's me the morning of the day of my wedding. I arrived about 1 hour late. If I didn't drink that last shot, I would not have destroyed that car in the park. And that's me the evening of the day of my wedding. If all votes would have been counted correctly, I would still be president. Donald Trump probably still yesterday. So what is the key? What are the two things that are in common with these questions? The first thing is that we are not able to answer them correctly, the first and the second. For what concerns the third, it has been answered correctly, I think, several times. But for the first two questions, how could we possibly answer correctly to that question? We can't, for a simple fact. We can't go back in the past. And so we face a problem. But we have to deal with the fact that we usually think and we usually pose questions in this kind of framework, in counterfactual framework. What could have happened? What could have been happened? And there's a second aspect in common that I would like to share with you that concerns the first two questions. The first two questions, I use the fact of the wedding because I would like to point out a simple but very important thing that of things happening in the past. Let's try to, we are quite a few persons, so today I will bother you quite more than usual, and I will ask you if you see a common aspect in the first two questions that is maybe interesting for the human way of thinking about all the fact that they are in the past underscores something very important to us. Can you guess what it is? Well, what it is a simple aspect. Okay, I already told this. The two aspects, the first aspect very important is that it concerns my single person, me, Marco Malvaldi, an identifiable human being, a person, a subject. And there's a second aspect that is quite crucial and quite important, and it is responsibility. Let's try to calculate the probability that I had a car crash being not drunk. For this, we need a little bit of notation, and I'm sorry for this. We will in a moment get rid of this. We will often in counterfactual analysis meet this symbolic notation, epsilon subscribe x. That means the outcome of epsilon when capital X equal x, when x was actually done. So the fact that I had a car crash, given that I was drunk, and this was something I did actually. So you can read it as epsilon, this variable, when do x, the action do x equal to x is performed. So we have a do operator, but it's on the it's not on the usual side. We're accustomed to see it. And so we cannot handle it easily, apart from different conditions, from particular condition. So we have to deal with this fact that we have a do operator on the wrong side. And this, we will see how to deal with this technically. But going on for the meaning, we are speaking of responsibilities. We're trying to understand the probability of having a car crash if I was not drunk, given the fact that I had a car crash and I actually was drunk. So I would like to compare an existing word, not a word of probability, an existing word, given that I have observation of what happened actually. So in this sense, this probability that we are trying to calculate here, and that is called the probability of necessity, tries to capture the concept of the but-for legal criterion. The victim would have not died but for the intervention of the defendant, of the people that is undergoing the trial. So This is very important. This kind of reasoning is very important in assessing responsibilities. So we are looking at the past in order to understand why something happened, not if X causes Y. We are, let's say, we are quite convinced that drinking affects the ability to drive. My question is different. If I did not drink, would I undergo in the same a car crash? This is a trivial example, but in other example, it may be not that easy. So we try to understand the probability of necessity, the probability of a do variable, of a variable conditioned on a do action, but actually we have no way to see this happening. We must condition on the probabilities, we must condition on the variables that actually happened. In this, I will try to go slowly, and I would like to have questions from you in the meanwhile between these two lessons, this and the following, because this, the correct interpretation of counterfactuals, is actually a difficult thing. It's something that mixes philosophy, natural language, and mathematical language, and it's quite easy to get messed. At least I was several times fooled by this part of mathematical causality, so I know perfectly that it's quite easy to get fooled. So do not, please consider the possibility that you get confused and puzzled by this first lecture, that you could not get immediately the technicalities of the part, because actually it's not straightforward even to get the grasp of this. So I'm trying in this first lesson to get the grasp of this, to get the grasp of the counterfactuals, and to try to let you see what can be done with counterfactuals. And we will see in the next lecture in detail how can we done, how it can be done. So let's try to build up a simple counterfactual analysis, and let's try to go through. And there are, if you know, I'm speaking about single subjects or single slices of population, that is persons or group of persons, and so on and so forth. And there are two ways to deal with a single subject. The first one, I express its behavior in a matrix of possible choices. That is, I deconstruct him. I deconstruct Marco in a brain, two arms, a mouth, a very big mouth, two eyes, and so on and so forth. And I try to understand how these parts combine together. Or I express, the second, I express a variable through a structural equation. And here, just I will begin my analysis of the counterfactuals in this second way, through a structural equation, because it's probably easier to see things through structural linear equations, to see how things actually work, even if, I repeat this, there's no need of the word linear when we are going to deal with real actual situation and probabilities. We will have a price to pay for this, but we will see in the following. So let's try to build up a body weight causal diagram. I would like to lose a little bit of body weight, so because I'm a little bit overweight, but this could not be the purpose for all people. For example, if you are a bodybuilder, you want to gain body weight. You want to gain muscular mass, not body fat, but you have to gain body weight. For me, I have to lose body fat, so I have to lose necessarily. I have to lose weight. So I can imagine a situation in which I have a common cause that is training time, the hours per day that I train, that conditioned two things. Actually, when I try to go to the gym and try to or begin to run or begin to do high intensity interval training, something strange happens to me. I duplicate the amount of food that I am convinced to need. I eat quite more. So training time is the cause of both the calories that I eat per day, my food intake per day, and of my body weight. Of course, not only the training time, but the kind of training. But here we are looking for a simplified scheme. Training time affects calories per day that I eat. Training times affects my body weight. And of course, the calories intake affects the body weight. Here, this is a simplified scheme, and we will see where problems can be. But let's try to express this causal diagram in terms of linear functions. If you remember, the subjects, training time, calories per day, and body weight are the variables, and the arrows are the mechanism. Here, I imagine to express the mechanism just in terms of linear functions. So the training time, UT, is an unobserved variable that is different for each and every participant in the study. For the calories per day has a single arrow pointing into it, that is the training time. So it will be a prefactor A, multiplying the training time plus a new C. It is, of course, the UC is a personal characteristic of mine. Is the, for example, the A may be a factor that counts the calories that I've lost, while UC is my personal feeling of hunger, or my personal feeling of hunger, or my status. B, if you see, of course, in the equation for C, it doesn't enter the term B, because B is conditioned only on training time and calories per day. So the body weight contains the training time and the calories per day multiplied by two factors, B and C. B is the kind, for example, the caloric percentage, the caloric need of the exercise that I'm looking for. For me, of course, is running. And I assume here, but I can assume a general exercise here. C is my metabolism, for example. So the calories per day multiplied by the metabolic factor, and UB is again my metabolism, is my personal way of dealing with calories, water, fat, proteins, and all the things that I lose. In order to understand, to build up a counterfactual, I would like to ask me what would have happened if I doubled my training time, if I trained 1 hour per day instead of half an hour per day, or if I more probably diminished halved my food intake during, for example, the Christmas time. So the first thing that you have to do is to measure me, is to get my personal data. So you have to take T, the time that I train, 0.5 hours, for example. You have to take C, the caloric amount that I get. And here I indicate it simply with 1 in order not to get messed by small numbers and or big numbers. So let's say that 1 corresponds to 2,000 calories, and B is my body weight. This is, of course, a quite unnatural assumption. Let's assume that I weight 1.5 kilo, 1,500 of kilos. So through the measure and through this equation, you can work out my idiosyncratic use. The unmeasured variables, the parameters that makes me the person that I am in this kind of situation. So you work out these 3 U and you obtain some numbers. Then what you're going to do is to take these numbers and substitute it into, you see, you take these idiosyncratic numbers for me, from Marco, and you substitute them into a new set of equations in which you substituted the equation for the calories by what I'm forced to do. Here, since I lose my mind just a little bit, I imagine that I'm not going to halve my food intake. Actually, I'm going to double my food intake. I'm stressed and I need to weight more. And then you work out. Of course, given the multiple factors, you will get an answer. Marco is going to exercise the same time. Marco remains the same person for the metabolic cost and so on and so forth. The only thing that changes is that he eats twice the thing that he was eating before. And the answer is that while before I was weighing 1.5, now I would weight 1.9. I would weight not the double of what I was weighing before. If you remember, I'm not weighing 3, I'm weighing 1.9. I'm weighing more, but not that more. So I was able to spot a counterfactual, given that I trained half an hour per day. What would have been the outcome if I had eat twice more? And this is the answer. So we have simulated this operation of halving the food intake. And I can represent this operation as the deletion of an arrow. In fact, I deleted the arrow of training time going into calories per day, and I substituted it, I forced it to substitute it into my operation. I don't know if this operation that I've done resembles you something, sound, makes some bell in your head ring. If it resembles something to you, and yes. Yes, is actually that. This is actually a do operation. And this is one of the motivation why it's really difficult to deal with counterfactuals, because we could be fooled by the fact that counterfactuals resemble do operation and sometimes are do operation, but are not always do operation. So the fact that sometimes simple counterfactuals or particular kind of counterfactuals are can be obtained by one simple do operation can fool us by this. Yes, okay, thanks. Andrea Pugnana wrote that the operation was do C equal to. Do the operation that C is equal to 2. And this is what we actually did. And we compared, in order to get this counterfactual, we have to compare the weight for do C equal to 2, less and subtracting the weight do C equal to 1, because I want to compare these two situations. I want to compare these two situations these two situations in order to understand what's happening. So sometimes we can deal simply with do operators. Sometimes it is not obvious how to combine do operations in order to get what we really mean and what we really want. So let's go ahead. In this case, for this counterfactual, and generally speaking, for dealing with counterfactuals, we follow a 3-step procedure. We will see in detail in the next lecture, but the procedure is the one we saw. We obtain the specific characteristics of the subject, Marco, so they use the idiosyncratic and observed variables by evidence. We measure and we work out by the equations. We obtain the use. Then we modify the model by removing the structural equations for the variables that we want to change, and we substitute it with our control value. And then we use the modified model and the value of U corresponding to the person to obtain the value of epsilon. This can be done, and this is what we do when dealing with simple counterfactuals. Just to make you see the backdoor criterion, that is the one that one of the criterion that we saw in the last lectures, can be interpreted in terms of counterfactuals. It means just that if a set of variables satisfy the backdoor criterion relative to x and epsilon, to my cause and my supposed cause and supposed effect, then it means that for all x, so for all the subjects or for all the groups that I can measure, the counterfactuals are independent of x if I can measure zeta, are independent of x given z. So for all x is the key then to understand the counterfactual. But we will dig into this deeper. Now in this lecture, I want only to give you a grasp of what can be done, because the situation is not always so simple. So let us to resume. Counterfactuals are not generally do operations, even if sometimes are accessible by a single do operation. They are rather combination of the results of multiple do operation. Through these multiple do operations, we build a fictitious different world, and in which we cannot usually access. if you remember, first I was trying to calculate the probability of having a car crash being drunk, of me being drunk, having drunk, given the fact being not drunk, given the fact that I actually had a car crash and I actually was drunk. But this was regarding me, not the general population. So when we deal with counterfactuals, we usually do not deal with a total population, but we deal with a particular slice of population. That is, it can be a person, it can be a group of person, or something else. But usually we want to see what they did in the past and if they could avoid it. Very important thing is that we cannot in general be sure to address a counterfactual even if we draw a causal diagram. Even this we will see in the next lecture, but I would like to point it out in the first. This is a situation that resembles the identifiability and causality operation that we did on the directed acyclic graph. If you remember, we were able to see that we can always identify a causal effect if the diagram satisfies some characteristics. But in general, this is not true. If it's possible to go on a bidirected path from the cause variable from the x to one of at least one of his child, then it's not possible. We will see that there is a similar situation even here, and that we cannot be sure to answer to a counterfactual query, even if we can draw a causal diagram. In the vast majority of cases, yes, but sometimes no, and it depends on unobserved variables, on confounders, on bidirected path. So let's try and let's dig into this, into a probabilistic case. This is an easy probabilistic case that we'll look for, and we will be able to work it out completely. And I will give you the study, the reference study, that is the study that you see here from Kugelgel, Gresele, and Bernard Scholkopf, pointing out a strange case of Simpson paradox in the COVID-19 case fatality rates. Actually, what is this Simpson paradox? If you look at the total of population, it seems that in Italy, comparing two equivalent amount of the spread of the disease and comparing the disease in China and in Italy, you would see that on the total mortality rate in Italy was higher than the one of China. It was about 5% higher. But if you were to compare, as we do in this graph, in which on the horizontal axis you see the years, the age range, and here on epsilon you see the mortality rate, you see that for each and every age, the rate for Italy is sensibly less than the rate for China. But when we look at the total, we see that mortality in Italy is almost the double that the one in China. So we know how this is possible. It's possible because the population, the demographic population of China and the demographic population of Italy are different. So we are not surprised by that. We already faced the Simpson paradox. But this does not solve our problem. We want to understand the mechanism by which it happened, and we want to understand if we could have done something or not. If there was the possibility to do something. So let's try to. As usual, since we are human beings, we start by asking questions, and these are the usual questions that you would hear in a talk show or in a TV show. The 4 questions that we address are: how much does fatality rate changes from Italy to China? And this is the simpler. Then the second is my personal one. Being in an age range between 50 and 59 years, would it have been better to get COVID in Italy or in China? This is something that concerns me. I am 48. I'm not between 50 and 59, but I'm a pessimist one. So I would like to see. I planning a travel. Planning my supposed past. Would it have been better to get COVID in Italy or in China? So it's a question that concerns a group of persons. Then there is the question. The third, given the demographic distribution of China, would China have had a better performance by adopting the Italian policies instead of the ones that they actually adopted? And here we come to responsibilities, here we come to policies, here we come to action plans. Could they have done better? Should they have done better? This is the question that we usually pose to ourselves. And of course, this is not a simple question to address, and we will see how, in this case, we can answer, but we can do something. I would like to make you note that addressing to this question is not possible because we would require to go back in the past. But it could have been a possibility. China could actually have done this action, the action that of following Italian policies. They did not for their reasons, but they could materially do this. The 4th question is really the fantascientific question, because if we were deprived of ethics, we could answer to question 2. If we could travel back in time, we could answer to question 3. But let's try to answer question 4. How would have fatality rate changed in China, having the same policies, but with the Italian demographic distribution? Here, in which way we could realize a geopolitical system in which the form of government is invaried, is the same of China. The history, the geography, the uses, the laws are unvaried, but the demographic distribution remains the same. But the demographic distribution is the one that I want, is the Italian demographic distribution. Really, really impossible to think how to realize this, but I can think about the possibility that someone, that a miracle, that something that I can't deal with, done this. And so I go into these questions, and I try to address these questions. So we are going to answer to this question. Of course, we need a causal model. And here is the causal model that the author proposed. We have a country that can be China or Italy. We have a demographic distribution that is for every age range, 0, 10, 10, 20, 20, 25, and so on and so forth. There is a relative population, a relative percentage, and then there is the mortality. Of course, the country causes the demography because of their policies, because of the way of life, because of the sanitary, of the national healthcare system, because of all the aspects that make a country a country. And of course, through the national healthcare system and through life conditions, it affects the mortality too. The demography affects the mortality, of course. If you are 12, you have a given probability to die. If you are 99, you have a presumably much higher probability to die by COVID-19. I remember here we are working only on COVID-19. But of course, demography do not causes country. It's not that when as you grow up, this raises your probability of becoming a Chinese citizen or an Italian citizen if you are Chinese. So we propose this causal model, and we will see in the next hour how to deal with this causal model, how to calculate the answer. And we first begin with the first question. How much does the fatality rate changes from Italy to China? And then, this is quite easy to see. This is the so-called total controlled effect. We compare two different imposed conditions. To answer this question, please notice that here I have do operations only on the right side. So the total controlled effect is the average value of the mortality, given that I do the country to be Italy, subtracted by the average value of the mortality, given that the fact that I do the country is China. So I pose me in Italy or in China, and I look at the total controlled effect. And here I can see, as we saw, that the total control effect is plus 2%. Why it was about 2% for China, it is about 4% in Italy. And we may hypothesize a reason for this. Can you hypothesize a reason for this? Someone of you, given the causal diagram that I showed, is able to hypothesize a reason why situation mortality rate in Italy is higher than in China, given the fact that I think let's be fair, let's try to hypothesize that the national healthcare system is on the same level in China or in Italy. Actually, probably is not like that, but let's try to hypothesize this. Why in Italy there's so higher a fatality rate? Can you hypothesize a reason? Yes, absolutely. Andrea Pugnana writes age distribution, and this is probably, we will see, but I know the answer, but we will see. The reason is that Italy is a country older than China. Average age in China is 35.5. Average age in Italy is 46.5. It's 10 years of difference. It makes you think. So, yes, please, Leonardo, just a moment that I will allow you to please, you can speak.
Hello, can you hear me?
Yeah.
I was wondering, in the case in which, let's say, for example, Italy enacts a policy that affects only a particular demographic in the mortality.
Mm-hmm.
Say, I don't know, people below a certain age are not affected by the lockdown, right? That would increase the spreading of the disease in particular age groups.
Yes.
Would the causal diagram still look the same? Or how do we essentially see when these essentially causes are combined in a sense, right? So there's an effect, but only on a particular subset of the variable.
This is a good question. I think that this is a question that we can think about in the pause, and we can try. All of us can try to draw a different diagram or understand if the current diagram is correct. But let me recap your question, if I understood well. Suppose that the policy, that different strata of the population do behave differently with respect to the law. This is what you're saying. That is, the young people do not respect lockdown while old people do, or am I losing something?
No, let's say, for example, in the causal diagram that we have, right, we have an effect of the country on mortality, right? Direct causal effect. And we suppose this is due to the policies that maybe have the health system or the policies of lockdown, et cetera, right?
Yes.
But I'm wondering, let's say that the effect on mortality is in a sense indirect because it acts only on a subgroup of people. Right?
Yes.
So
yes.
It would not be an effect on the total mortality. It would be on the mortality only of that subgroup of people, right?
Yes. Yes. In this case, the graph would still be correct, because imagine to visualize it. Okay. Imagine several parallel different graphs. Each of these graphs for a different stratum of the population, for a different age, okay? Then you would see, and you can imagine a different mechanism, a different functions pertaining the arrow that joins country and age, okay? So for example, country affect me as being an almost 50 years old writer. Almost nothing. I stay at home but it affects quite a lot young people, because by lockdown, they're not able to go anywhere, okay? So if the policy of a country is no lockdown, it will affect quite a few people staying home, all the poor old people staying home writing, but will affect much young people. And then you will see a stratified difference that will get you a difference. Whether this causes a total effect that is worse or better, this is given by numbers. But as we know, this is not our purpose. But my opinion is yes, in the case that you mentioned, the diagram would be the same. You don't have to imagine these arrows pointing for country to age as monotonic arrows. That is, they are they can be quite idiosyncratic functions of the age, or even step functions of the age, if you want to imagine them as functions. Okay, I don't know if I've been
No, very clear. I was just wondering, in the case, for example, in which maybe there is a mediation, then that might be different, right? Because then maybe the demographic might have an effect on the mediated path that goes from country to.
Okay, then you can, of course.
So, for example, maybe I make a clear example is, let's imagine, for example, the healthcare system, right? But we know that maybe the capacity of the healthcare system depends on demographics, right? Because of course, if you have older patients, you're going to have more patients. So the capacity that you have will be filled up quicker, right? So in that case, the demographic actually affect the healthcare system independently of the way the country does, right? And then in that case, that mediated effect would imply that there should be an arrow, right, from, let's say, demographics to healthcare system.
Yes, you mean I would have to insert another variable that is age, the healthcare system, and then two arrows, one pointing from age to healthcare and one pointing from country to healthcare.
Exactly.
And then, of course, healthcare to mortality. Okay, so this would be a refined graph that should work better. In my opinion, this would be an improvement of the model that would work better for two reasons. The first one is that, if you remember, saying it in a George Orwell more arrows bad, more variables good. So the more variable you are able to measure and to separe, if you're smart enough, if you draw the causal diagram, the more variable you can measure, the better your analysis. Even remember, if you do the diagram, if you don't add them, just like the more the better. So this would be better, and it would be better because we are able to draw causal arrows from country to national healthcare, from age to national healthcare, from national healthcare to mortality. So we would obtain a complete, that is a causal sufficient graph. You see that if I use your hypothesis, I have no bidirected arrows, and so I know that I can work completely with my do calculations in this graph. And we will see in the following that when I have this kind of graph, even my counterfactuals can be calculated completely. So when I have this kind of graphs, I mean, the one in which I have only directed arrows, I am sure not only that I can calculate the do operations, but even that I can calculate the counterfactuals. So in this sense, it would be an improvement. And it would separate, for example, the effect of the country by means of the healthcare from the effect of the country by means of laws, lockdowns, or other policies. So in this sense, it would be an improvement if you're able to measure that variable, healthcare. So in this sense, I can measure country, Italy, China. I can measure age. I can measure mortality, yes or no. But you should find a feasible measurement of healthcare.
Right, but maybe then just to clarify, then in the question that I would have, let's say that I cannot observe the healthcare. In that case, let's say the reduced graph would be the one that we have, right? Yes. Even though this mediated interaction would no longer be there.
Exactly.
Okay.
No, sorry, because in this case, you can imagine a bidirected arrow that goes, sorry. I was, the fact is that you have a particular, you would have a bidirected arrow unobserved going from country to age. So you will still have a directed arrow, country age, but you should add indirected, three indirected arrows: country age, age mortality, and country mortality. So the graph, I will draw it analogically. In the case that you state, okay, the graph would look like this. Okay, imagine that in the middle there is the variable healthcare system. I have so I'm not pretty sure of what I'm saying because no, sorry. Only the direction would still be from A to M and from C to M. Let's try to work it out, and let's see if I can convince all of you. Okay. Let's say that this is the starting hypothetical graph that I want, okay? Do you agree?
Yes.
Okay, so you see that the direction is from A to H and from H to M. So in this case, the arrow still goes from A to M. So the direction is the same. So even from C to H and from H to M, so the direction is still from C to M. But H is a collider from for A and C. So in this case, I would have a second arrow pointing from A to C. I'd had this in my opinion.
Right. That's kind of what I was wondering. When you have this kind of effects that you're supposing that you cannot observe, how would that change the original graph?
Well, in this situation, you can imagine that we are really in a mess. If we take your model as good, you can imagine that all the things that I'm going to say from up to now would be nonsense, because there is a bidirected edge that goes from the country to the age. So in the next future, I'm trying to evaluate the policy of the country. In the next hour, I'm going to evaluate the policy of the country to mortality. But since age is a child of country, I could not make the observation that I'm going to do right in the following. The consideration that I'm going to do in the following are based on the simplified model that you saw earlier. Thanks for this interesting question. I'm trying to work out, but it makes sense. It makes sense for me. What if I control for age? Asks Andrea. Then Andrea, this will be the if I control for age, I obtain what I call, and I will show it immediately. I will show it immediately, and then we will have a little. No, yes, I understand. As Andrea is asking, if I control for age, I did not get why you can't retrieve the effect. We have to be clear about which cause and which effect we are looking at. So if in my original graph, in the only directed graph, I control for age, I obtain the so-called direct control effect. I do control for age, for each group of age, and I evaluate the probability of mortality if I do the country, if I force the country to be Italy and the age to be A, and then for my given age group, 50-55, I obtain that the probability is less. And for each and every age group, I obtain that the mortality is less. But what we are saying here, Andrea, is that the situation would change if I would like to understand the effect of the country on the mortality, because I'm not sure that let's say the healthcare system, the unobserved variable that I see in my graph, being a collider, could open up information between country and age. So it would make me make consideration about partial populations. In this fact, when you have an unobserved collider, it can work as unobserved common cause. So the fact is that, why do I say so? Because we're speaking about mortality of people being diagnosticized with COVID-19 that went to hospital. According to the kind of healthcare system that you have, you can possibly miss many people having COVID-19 that are not diagnosticized with COVID-19 because they could not reach the hospital or the triage or the diagnostic situation. So in this sense, I think that that considering into play the healthcare system, in this case, if we consider people diagnosticized with COVID-19, that is the purpose of the study that we are speaking, can open up mess in the sense that we have an open collider, that is the diagnosis, the fact that they have been diagnosticized with COVID-19. This is a very interesting question, and you see that is interesting by the fact that we are not clear still about among us about how to deal with this. I suggest to refresh our brains with a coffee and see you in 5 minutes in order to go ahead, and if we want, we can think about this in the following weekend and in the following lecture. But you see that causality do not mean I'm sure that I'm getting all the answer. I have to build a model and I have to test if my model is correct. So a possible way to test if my model CAM is correct would be to check if there is conditional independence. So this is a thing that I hadn't tried on the original data of the paper, and it can be worked out. So for sure, a thing that I can do is see if there are hidden dependencies between country and age, between, let's say, age and country, so that age shows up in this particular population H shows up as a parent of country. And so in this case, we would see an unrespected conditional independence. So let's refresh our brain for 5 minutes, and then we will go on with the counterfactuals, questions. See you in 5 minutes. Okay, hello. So let's, yes, immediately a question, wonderful. Yes, just a moment that I allow you to, I give you the power to speak. Okay, please.
Yeah, it's
no, sorry. Yes, you can speak. Sorry.
I can now, right?
Yes.
You hear me? Yeah, perfect. Yeah, I was wondering, well, in the example that we were designing with the healthcare system in the middle, like as slider between country and age, would it be? I don't know if it is still possible, maybe assuming that the relationships are linear, to retrieve the total effect with multiple steps. I don't know if this is something that we can do or not, because I think that from the way we are designing it, I would say it might be possible with multiple steps, but I don't know if this is actually something that we can do.
My answer is that I don't know, because I'm not that expert of linear models. So I write down and I will control my impression. But take this as an impression, is that probably no. But you have, I think that you have the possibility, if the relation is probably, because it could be possible if it is monotonic. So if it's
that's
monotonic, it's monotonic. So no, probably yes, but I have to control it a little better, because at the moment I'm not able to answer you. I will check and encourage you to do the same, but I will check. Thanks
a lot.
Okay, so let's go further and let's look at what else we can do. We were before dealing with the direct controlled effect, CDA, and we saw that even here we have a situation that we can afford. We have an average value of the mortality doing, the country is Italy, and the age is my given age, minus the average mortality doing the countries China and my average age. So here, for the controlled effect, when you look for the word control, it means that I am actually controlling on a mediator, on a variable. And here I have my well behaving on the right side, where I can deal with them. But let's look at this other, and of course, this is the definition of the CDA. The CDA of a binary treatment on an outcome, y with the mediator x, is given by this interventional contrasts. That is rather intuitive. I take the expected value doing the treatment. In this case, the treatment is the country and the mediator, so the age range, minus the expected value, given that I do not give the treatment, so I switch country in this side, and for the same age. So I watch for that particular value of the mediator. So let's try to look at a different question. Given the demographic distribution of China, would China have had a better performance by adopting the Italian policies instead of the ones that they actually adopted? Here the question is a little bit different, because we see that we would like to intervene on China and not on Italy. And we would like to intervene by calculating the effect of something that China did not did. So we are in the field that we were looking before. We have a do, but we have a do on the wrong side. The definition of this effect that we call the natural direct effect, is given by this counterfactual contrast. Remember, a counterfactual contrast is always the difference between an expected value and another expected value. But in this case, the first expected value is the expected value of epsilon, given that x was 0, given the x when the treatment was 0, when do t equal 1. If you remember the notation, this means that I have to apply, to compare two different policies accessible to the government, the policies of China applied to Chinese people, and this is the second term that you see here, that is actually what happened and for which I can measure probabilities and distribution, and the policies of Italy applied to a Chinese demographic distribution. So here I have a do here, but if you remember the meaning of this notation, it means M do demographic distribution of A is the one of China. So here I have a problem. In this case, the calculation is possible, and is possible because of the characteristic of the graph that we saw earlier, and we will see in the next lecture how to do it. But for the moment, what I would like to point is that it's possible to do this calculation. So to calculate the effect of something that actually didn't happen. So we're not calculating the effect of a redistribution. We're calculating the effect of something that wasn't performed. We're calculating a do on the left side and on the right side. And this is exactly the definition of the natural. In this sense, I say natural because we don't control for the mediator. The population, the demographic distribution still remains the one of China or of Italy. I just imagine to switch governments, to switch policies, or better, to make China copy the policies of Italy. And I ask it with regard to the past. So I ask myself, if China had did like Italy, would things have gone better? And the answer is, according to our causal model, yes, a little bit yes. If you remember, mortality would have been less than 0.8%. So it is possible to answer these kind of questions. So the various components, as I was saying, the expected value of the mortality given the hypothesis, the mortality that China would have had if the hypothesis on the right would be true. So the expected mortality on the population of China doing like Italy is the mortality that China would have had if Italian policies would have been adopted. While the third, the expected mortality of China doing the policy of China is the mortality that China would have had, but in this case had actually, because we can measure it if Italian policies would have been adopted. In this case, the do operation and the conditional operation are exactly the same thing, because there is no backdoor path between country and mortality. So let's, of course, this kind of analysis is not only a retroactive analysis. Using these results, a third country, for example, Spain, for example, Germany, could decide which policy to apply in the future based on its own demography. But in order to decide for the future, the best thing is to understand properly the past. You, by studying history, you can understand future, but you have to understand history and not just to read it. And then the fourth question, that is the fantascientific one. How would a fatality rate changed in China having the same policies, but with the Italian demographic distribution? So imagine that you switch in the past the two populations with no consequences at all. And or better, you don't switch population, you just re-equilibrate the population, because of course they're Chinese, they're of a slightly different ethnia. So we want to change only the demographic distributions, not the population. So this is absolutely an unfeasible task. But in this case, we can still answer. This is the natural indirect effect. We compare two situations. Not accessible to any kind of experiment, because here, if you see the two expected values are one doing the mortality of China, doing that they have the demographic distribution of China, and one is the mortality of China doing the demographic distribution of Italy. We have two different doing into different position. And here, so this experiment equals to the question, if in China they have our demographic distribution, if they were old like we Italians are, what would be the situation? And the answer in this case, where I have Markovian graphs, perfect Markovian graphs, and in which I have only directed arrows, I can calculate this, and I can get to the correct answer, which is 3.3% worse. So this is the kind of thing that we can ask, and I would like to point out this is the definition of the natural indirect effect, in which we don't control the mediator, which is still distributed, so we don't look for age ranges, but for a distribution, but we put the distribution in a place where it could not have been. So my point in this lecture is not not particularly of technicalities. We will see in the following lecture about technicalities, about how to calculate, but is of meaning. If we are able to build up a causal model, we can take questions that are rather mad to think about, to the possibility of answering it by experiment. Actually, you can't imagine an experiment that could deal with this situation, but you still can answer by means of applied statistics. You have a bridge, an imperfect bridge, or better, an incomplete bridge between the natural language and between the mathematical language. This bridge do not always works, because there are situations, there are confounded situations, common cause or uncontrolled situation in which this can't work. But if you can draw a graph in which all the arrows are directed, or in some cases, and we will look in the following which cases, you can draw a graph with bidirected paths. In some of the cases, you can answer this kind of question. The what if in the past had happened this, or what if this impossible situation would have realized? So if we can express it in natural language, we can most of the time answer it even by mathematical language and by probability, not by linear modeling, but by probability only. And this is resuming what I was saying. The second two questions, the one that we were looking, cannot always be answered, but can always be answered if there is causal sufficiency. So if no unobserved confounders are involved. And here, I finished the presentation and the lecture. It would be not probably not the case here to begin with the technicalities that we will see in the next lecture. But I exploit this 10 minutes now of time that are remaining to ask if there are questions, and if there are no questions, I would like to point you a little example concerning responsibility and probability, and why we should care about this kind of objects. So if there are not questions, I would like to tell a bit about this story. So we spoke about responsibility, and of course responsibility often calls the law. We're not discussing here about the possibility of punishing someone based on a probabilistic calculation. We are not still there, and I would find it at least questionable to convict someone on the basis of probabilities. But in the US, in the United States legal system, this is a practice that is going to take place, is the practice of solicitors, of lawyers, to use probability in order to speak with the jury, in order to speak with the person that have to understand. So Why I will tell a story, and then I will try to give you a motivation about the fact that I give this story. Suppose that I have a murder attempt. A person, me, that shot another person, my mother-in-law, the first example that came in my mind. I miss her completely, and she runs away. As she runs away, something incredible happens. A piano that some workers, an instrument, a musical instrument, a piano, a full piano, 3 meters length and average a ton of weight, that some workers are translating from the 10th floor, falls. The piano falls and hits my mother-in-law, killing her. So the question that I would like to ask you is, am I guilty of attempted murder? So must be charged of murder. The victim, my intended victim, is dead. But did I directly cause the death? I missed her. I shot her, yes, but I missed her, and I wasn't able to predict the fact that a piano was falling. So yes, attempted murder, yes, but probably murder, no. What is your opinion in this case? You can answer this just by chatting, but what is your opinion? It is an attempted murder or a murder? Should I be charged for attempted murder or for murder, since the victim is dead? Attempted murder, says Leonardo, and I agree. And most people, I think that if someone disagrees, please write, but I think that most people agree that this is an attempted murder. Well, now I change a little bit. Now we are not in a, we are still in a urban context, but we are near to a highway, let's say in an autogrill, in a stop place on a highway. I shoot my mother-in-law. I miss her. She runs away, but this time she goes through the street and comes up, and it ends up being hit by a car passing on the highway. I shoot, she runs away, and she comes to be hit by a car on the street. Now I ask you, what is my charge? Attempted murder, and she dies. Of course, it's a happy end. The mother-in-law dies. I ask you, it is still attempted murder? Is it murder? Am I tempted to change my mind somehow? What do you change? Some of you do think before was attempted murder, but now it is murder. I am responsible for the death of this person. What is your opinion? I can hear your fingers cracking. Well, is there someone that thinks that now it is actually a murder? Or you are still convinced that this is an attempted murder? What would you charge this person with? Well, my personal view is that my opinion changes. I have and this, my sensation is that my opinion changes, and I would like to say why my opinion changes. When I shoot my to my mother-in-law, yes. You say, Leonardo says, if the location chosen for the shooting was purposefully selected, then I would say murder. Otherwise, no. I have a different opinion. My opinion is that I should be charged by, I don't know the term in English, omicidio colposo. That is, I'm not directly responsible for the death, but I was able to predict the outcome. The sense of what I'm saying is this. You see that you already changed a little bit your mind. Of course, is not let's say omicidio premeditato. It's not a full homicide, but for me, many judges and some of the lawyers that I've spoken agreed with me, while some other not. Would charge the defendant with omicidio colposo. Why is that? And why this is my opinion too? And we will try to discuss. Try to order the probability of the event. A piano falling, a shoot directed towards someone, a walking person that has been hit by a car. This is rather a seldom probability. A piano falling happens more seldom, happen less in frequency. That's sorry, I answer and I arrive. Sto facendo lezione, arrivo. Terribly sorry for that. The piano falls, very low probability. Being shot, it may happen. It has a higher probability. A walking person hit, a higher probability. In the first case, the probability of the killing accident, of the killing event, the piano, is considered less frequent than my action, my shot. It happened. I wasn't able to predict it. While in the second case, the probability of being hit by a car is much more than the probability that I shot someone. I could have predicted. So I was able to face in my mind that if I shoot someone close to the highway and miss him, if he runs away, he could be hit by a car. So I could have predicted it. So what is the point of everything? In each case, the event that we consider the cause, the but-for cause, is the less probable one. In our mind, the event, the but-for event, is the less probable one. So in the first case, my action did not directly cause the death. The piano is not related to my action. But in the second cause, but of course, I shot, and without the shot, the person would probably be alive, but I wasn't able to predict it. In the second cause, I shot and I was able to predict the outcome. So we go in a complicated framework. As you see, we're not agreeing on this thing. Many of us have the intuitive feeling that the cause, the underpinning cause, is the less frequent one, is the less probable one. While, as we saw, a cause and effect is a different matter. So it is very important when we do causal calculation that we are able to communicate correctly our causal model, and we speak clearly about why we did choose that model and how probability drive our way of thinking. Because when you will face decisions, often when you speak of probability, people watch you and says, how can you decide this by probability? And well, often without even thinking about it, we decide using probability. We're just not aware of this fact. So, this is the end of this lecture. In the following lecture, we will go dig into the technicalities of the counterfactuals. And I think that there is room for discussion the next time. So please prepare questions, things of which you are not convinced, things that you would like to point out, and we will watch them and try to see if all together we can understand this properly. And I thank you for your question and for your attention, because as you understood, I'm still studying and trying to understand some aspects of causalities. So all your questions and all your doubts make us advance all together. And this is not just for sake of saying, but is actually the truth. So thank you very much, and see you on the next Tuesday.
Thank you, Marco.